He's muted.
He is muted.
Aaron says they also don't need, so they're not hearing you.
Oh, they're not hearing me.
Yeah, but we hear now.
Oh, okay, great.
Okay, great. Sorry about that. I had to unmute.
Thank you for the useful text communications. Do you want to tell Kyle one more time?
Oh yeah, Kyle, I'll interject if you don't mind when you have about 2 minutes left, if that's okay.
Okay.
Can you hear me now?
Sounds good. All right, should I go ahead and share and roll?
Yeah, that sounds great.
Okay. All right. Well, hi, everybody. I'm Kyle. I'm a postdoc at UC Santa Cruz. Very to not be joining in person. There's unfortunately an exoplanets, long period planets conference that directly overlaps. Also just note that when we were testing, the slides are lagging by about 5 seconds right now. So this might be kind of like one of those old movies where the audio and the video don't exactly line up. But nevertheless, I'm very excited to talk about my bread and butter survey that I led as a graduate student focusing an exoplanet imaging survey targeting accelerations between Hipparcos and Gaia. So over the past couple of decades, the exoplanet imaging community has assembled a sample of about 30 directly imaged giant planets on wide Earth and about 100 or so brown dwarf companions. And one of the main drivers behind this effort has been tackling this question of how these objects form, right? These wide orbiting giant planets and brown dwarf companions are often kind of a gray area where it's not immediately clear whether they formed through a bottom-up core couple accretion process, maybe gravitational instabilities and massive protoplanetary disks, or sorry, are the slides changing? I'm just looking at the.
No. We're still on your
the slides have not changed.
No,
okay.
yeah, not yet.
Okay, so we might need to make a change here because it does not. Yeah, do we want to make copy and we can just move forward, or I can just say when to click?
I think he's asking if we have a local copy.
Oh, okay, yes, I will. Let me try to pull this up. We do. 1 second. But now I will need to, okay, here we go. Yay, thank you. Okay, hold on. Oops. Okay, I can try to do this. Okay, yeah, if you just tell me, I can click to the next slide. But you might be frozen.
Okay. All right. Okay. So sorry about the technical difficulties, everybody. Are you able to? Oh boy. All right. I will go ahead and stop sharing video here. Can you hear me?
Yep, you sound good.
Okay, great. All right. I'll go quickly then here. So go ahead and click through to the end of this slide. One of the fundamental questions that we're tackling as an exoplanet imaging community is this question of how these objects on wide orbits form. And there's up core pebble accretion process, maybe top-down formation through gravitational instabilities, or maybe some of these wide orbiting supermassive objects are the lowest mass products of the formation process. Now, in order to diagnose and we need to understand the types of objects we're discovering. The challenge is that for most imaged exoplanets, we don't have direct measurements of their masses. So go ahead and click through to the end of the next slide. So this plot here shows the current sample of imaged brown dwarf companions in gray and imaged exoplanets in orange. For most of these points, the mass determinations are highly uncertain. They're inferred through evolutionary models, incorporating their luminosities and their ages. And so that means that in general produces highly uncertain. To closer in orbits, go ahead and click. we have the reflex motion that objects induce in their host stars gets larger. And this has been used, especially in the last few years, to obtain dynamical mass measurements, direct mass measurements for a small sample of mostly brown dwarf companions, as well as a handful of planets as well. Go ahead and click forward. All right, yeah. And these points, these brown dwarf companions and giant planets, really offer us one of our best views into the planet formation process. Go ahead and click forward. But if we want to really understand planet formation through these dynamical masses, we just need more of these systems, right? Are in the planetary regime, we only have a handful of them. And so a promising strategy in the last few years has been using astrometric information from Hipparchus and Gaia to select the best targets for imaging new planets on wide orbits. The idea is that wide orbiting giant planets and brown dwarf companions will induce a small change between these two missions. And so one can use this to conduct an informed targeted search for planets that we can go and directly image by specifically focusing our exoplanet imaging search on stars that show these small astrometric accelerations. Go ahead and click to the next build. These astrometric accelerations also enable these rare and valuable direct mass measurements that we can use to contextualize these discoveries and ultimately tie their properties back to this question of their formation. But how do we pick the best targets for an exoplanet imaging search? Go ahead and click to the next slide. So given an astrometric acceleration, we can determine the companion masses that are consistent with causing it as a function of separation. And this is sort of shown in the blue curve here. And you can see the degeneracy that we have where given an acceleration, we don't know if it's a closer separation, lower mass thing, or a wider separation, higher mass thing. Now this star actually corresponds to a brown dwarf companion with a direct mass measurement. And so if we go ahead and click to the next build, and splash up the dynamical mass and separation of this object, we see that it lines up quite well with this prediction. And so with these predictions in hand from these astrometric accelerations, triage potential targets for an exoplanet imaging campaign. For example, if we have a star whose astrometric acceleration prediction looks like this, click to the next build, we know that its acceleration could be produced by a brown dwarf companion within 500 milliarcseconds. Go ahead and click. If we have an accelerating star that looks like this, go ahead and click. We know that we'd want to avoid it for an exoplanet imaging search, as its acceleration could only be produced by a binary. Go ahead and click to the next slide. But if we have an accelerating star whose prediction looks like this, we know that its acceleration, go ahead and click, could be produced by a giant planet within a separation of 400 milliarcseconds. And if the star is young, meaning favorable sensitivity for imaging new planets from the ground, this could be a really promising target for an exoplanet imaging search. And so over my time as a PhD student, I led an exoplanet imaging search doing just this, exploring stars that show these small astrometric accelerations between Hipparchus and Gaia to maximize our efficiency of imaging new exoplanets. It's a program that we launched back in 2019 in the Gaia DR2 days, the second data release of Gaia. Since then, we've continually updated our target selection, our sample, all with the goal of efficiently imaging new exoplanets. So I'll just focus on the most exciting discovery that has stemmed from this campaign, which we are just now wrapping up here. And that discovery is AFLAP-B. Go ahead and click to the next slide. So AFLAP-B is an imaged exoplanet that we discovered through this program that is the lowest mass imaged planet that has a direct dynamical mass measurement. This is a planet that we, GIF here shows the imaging that we obtained of this planet. We obtained on Keck. You can see the orbital motion that the planet tracks out over the year and some change between these observations. Jupiter's orbit here just to give a sense for the scales that we're probing with this discovery. The separation between AFLAP-B and its host star is very similar to the separation between Saturn and our sun. And so one of the most exciting elements of the discovery of this planet was that it was shared between 3 teams leading independent programs, all following up these stars that have these astrometric accelerations with different data sets, with different instruments, different time baselines. And so this means that this planet has been really well characterized sort of right from the outset. Go ahead and click to the next build. So we image the planet with Keck, which gives us L-band photometry. We measure an L-band contrast of 10 magnitudes, a separation of 350 milliarcseconds. 3 builds. The star is orbiting a sun-like host star in the Beta-Pic moving group, which gives a precise age constraint of 24 megayears. It also follows in a tradition of planets being imaged around stars that host debris disks. Go ahead and click to the next build. Just to give a sense for the astrometric acceleration signal, so the astrometric acceleration for this star is 2.5 meters per second per year. So this gives a sense for the physical scales that you need to be sensitive to be able to recover a wide orbiting planet like this. And go ahead and click to the next build. So the big result is that updated orbit fits are showing this planet of 3.5 Jupiter masses, which places this planet as the lowest mass imaged exoplanet that has one of these direct mass measurements. Go ahead and click to the next build. And so here's where A-flat-B falls on the plot that I showed earlier of the masses and orbital separations of the current sample of imaged exoplanets and brown dwarf companions. And I really like this plot because it really showcases that with discoveries like A-flat-B, we're marching closer and closer to imaging true analogs to the giant planets in our solar system. This has been a really exciting discovery for the imaged planets. Go ahead and click to the next build. And so it's been a couple of years since the planet was discovered. Since then, the community has characterized A-flat-B at a record pace. Go ahead and do, I think, 5 builds. There's been atmospheric analyses. There's been archival recovery of the planet, GWST observations, gravity observations. I think we have one more build in high-resolution spectroscopy. Spectroscopic observations. It's been really extraordinary how rapidly this planet has been characterized. Go ahead and click to the next build. And so I'll just really briefly here hone in on one of these follow-up programs, a program that I led, attempting to obtain JWST imaging of the planet. Go ahead and click to the next build. And some of the motivation for this program really stems from some of these early atmospheric analyses of the planet that showed a potential enhancement in its atmospheric metallicity. And so with all of this in mind, go ahead and click to the next 2 builds. I got really interested in extending the SED of this planet longward into sort of longer wavelengths that are really best covered with JWST. And so to this end, I co-led, along with William Balmer, a graduate student at Johns Hopkins, a JWST Director's Discretionary Time program in Cycle 2, with the goal of recovering this planet, despite it being at a really close separation to be recovered with JWST. It's sort of 2 resolution elements away from its host star. But another way of highlighting this, if you go ahead and click to the next build, is that the coronagraph at this separation blocks out most of the light from the planet. So this image here shows imaging of a wider separation planet taken with JWST in the same. And even at that wider separation, go ahead and click to the next build. They or 10% of the light from the planet. But if we march our way inward, go ahead and click, I don't know, like maybe 3 builds in. That's the separation where 75% and 25% of the light is let through by the coronagraph. Go ahead and do one more build. Here's the separation where 10% of the light is let through. And then one more build. This is where A-flat-B's orbit falls, or A-flat-B falls. So we're trying to image this planet 2 lambda over d away from its host star in a regime where we're losing 9 out of 10 photons to the coronagraph. And so needless to say, this is a really challenging planet to recover with JWST. Go ahead and click to the next slide. Here's a prediction of what we thought the imaging of the planet might look like. We never know for sure until you get on sky, right? And this is a very challenging regime that we're operating in. Okay, so this is the prediction, and go ahead and click to the next build. And this is what we imaged with JWST. We successfully recovered the planet at a high significance, right where we expected it to be at its current separation. Go ahead and do four builds. Right at the separation that we expected it to be, 10 mags contrast. This is an exciting achievement for JWST coronography at close-in separations. The chronographic transmission that we're correcting for here is 7%. And if you go ahead and click to the next build, this is just a highlight. This is just one node in this story of JWST outperforming expectations at close-in separations for imaging exoplanets. And so go ahead and click sort of 2 builds forward. Yeah. We found that the planet was relatively faint at 4.4. That is consistent with some combination of strong disequilibrium chemistry and elevated atmospheric metallicity. Go ahead and click 2 builds forward. So I just want to quickly highlight the orbit of the planet. We of course carried out an orbit fit with our initial discovery paper, but there's been some updates since then, including an archival recovery of the star in 2011 data. Go ahead and click where the planet's on its other side of the star, do 2 more builds, and gravity observations of the planet. And so the orbit of the planet is pinned down really well. Go ahead and do like maybe 3 builds. It has a semi-major axis of 9 AU, a circular eccentricity, an orbital inclination that closely matches the projected inclination of the host star. 2 more builds. Dynamical mass that's consistent with evolutionary model predictions. And yeah. And so go ahead and go to the next slide and just go through all of the builds on this slide. So when you combine the atmosphere of this planet, it is consistent or suggestive of the planet forming through a core accretion formation channel. And so to go from the discovery of the planet just 2 years ago to assembling such a well-mapped FCD in orbit to be able to make this kind of inference about its potential formation really speaks to the science that we can do with these exoplanet imaging searches informed by astrometry. I'm very sorry about the technical issues. Thanks for working with me here. If you go ahead and just go to the next slide, I just have a few summary points to splash up there. Thanks so much.
Thank you, Kyle, and thanks for coaching me through to your builds. This looked great. Any questions? Like a quick question before we go to the next presenter? Okay. If not, for the sake of time, Kyle, we'll let people message you directly for any questions. Oh, there is someone. Sorry. Oh yeah, go ahead. Sorry, Kirsten.
I was just going to ask, aside from this planet, are there any others that may not be as low mass or that would be an interesting next step to look at as well?
Did you hear this, Kyle? Or do you want me to repeat?
Yeah, that's a great question. So the question is, are there other planets that are low mass that would be interesting to look at? So there have been other discoveries through these exoplanet imaging surveys targeting astrometric accelerations, including brown dwarf companions. We've discovered 1 brown dwarf companion, but the really exciting direction looking forward is the next data release of Gaia is really going to expand the target list and the capability of these sort of targeted exoplanet imaging surveys significantly. And this next data release is scheduled to come out. It's currently expected to come out in December of 2026, so a little over a year. So we're very excited about the potential to really significantly expand the sample of these planets with dynamical mass measurements.
Great. Okay, thank you so much, Kyle. And now we're going to move on to our next presenter. Keming Zhang is going to tell us about free floating planets and gravitational microlensing. Let's see, I guess I can switch to display 1. Oh, okay, it's already happening. Okay, Keming, you can unmute when you're ready.
Can everybody see my slide?
Yes, we can.
Thanks. So my name is Keming Zhang. I'm a first-year second fellow at MIT. Today I'm going to be talking about some of my ongoing work on the topic of free-floating planets. So to start with, I think one of the most exciting developments, especially for planets, is the launch of NASA Roman Space Telescope in just a little over a year, maybe less than a year. It's happening real soon. And this figure shows comparison of planets detected by Kepler versus planets we expect to detect by Roman. Y-axis shows the planet mass, and the x-axis shows the planet's major axis. And the point to emphasize here is that most of the planets that we detect by transit orbit close in, and those are short period planets. And Roman, on the other hand, the planet that we expect to detect by Roman using microlensing really complementary. And it's interesting to see that the planets that we expect Roman to detect span a really wide range of 7 major axes, all the way down to 100 AU, and even further. It's just the plot is cut off there. And so to start with, how exactly do we detect such wide orbit planets using microlensing? And a way to think about microlensing is that close alignment between two stars causes the time variable magnification. So the left side, so the two figures shows two different microlensing events detected by the Ogle survey more than a decade ago. And the left shows the planet detection at projected separation of 4 AU, whereas the right-hand side shows a planet at a much wider separation of 18 AU. In both cases, the way to think about microlensing is that we usually think of the lens system as fixed, and the background source star, which is the star that got magnified, passes behind. So in both cases, the source star passed first in behind, very close to the planet, and then its host star. And of course, the wider the separation, the wider the two peaks going to be separated by. And for the 4 AU case, the planet peak occurred, let's see, around 2 months before the peak magnification produced by the host star. And for the 18 AU case, the planet signal preceded the host signal by nearly 200 days. And what's interesting about the second event is that 2 years later, we actually the Ogle survey detected another peak, which was interpreted as a binary companion to the planet's host star. And so this is the same event, but with the source trajectory relative to the lens system illustrated. So the red line shows the source star's trajectory, which passed really close to the planet first, and then near the host star, and then a binary companion to the host. So as you see, in order to detect this wide orbit planet, it really requires these exact alignment of the geometry, basically the direction of the source trajectory with respect to the planet's axis. So on the other hand, if the source star crossed the planet on any at a other orientation, then we will only see the magnification signal from the planet lasting oftentimes less than a day. And apart from the short blip of magnification, we don't see anything else like within the time span of decades. So how do we know if these short magnification microlensing events, how do we know if there are bound wide separation planets or simply free floating planets? And before getting into that point, basically, so the current statistical analysis of the microlensing timescale distribution showed that these short events representing free floating planet candidate outnumber stars in our galaxy by up to an order of magnitude. So the two figures are the microlensing event timescale distribution from two different surveys, and both show an excess of events shorter than a day, which are not accounted for by the known population of stars and brown dwarfs in our galaxy. And of course, with the caveat that these free-floating planet candidates could also be just on very wide orbits. So the basic idea, so the only way to distinguish between the two scenarios is that if the planet is a bound planet, we should be able to see the source star, the host star. So typically for bound planets, at the time of the event, the source and lens star, the lens star is just the planet host. So the source and lens star is perfectly aligned during the event. And the scenario is not stationary, so they move apart from each other at a few milli arcseconds per year. So this example shows that the lens star was resolved from the source star after 10 years of the event, and they're separated by 40 milli arcseconds. And because of how slowly they move, the typical proper motion are, it really requires high angular resolution imaging. In this case, using Keck adaptive laser Geyser adaptive optics. And after detecting a detection of the host star, will also measure its apparent brightness, which also serves to refine the physical properties of the system. And there's one caveat for bound planet is that not all planet hosts are bright. So, more than 10% of microlensing events are thought to arise from white dwarf lenses. So currently, two microlensing planets have been inferred to have to orbit a white dwarf. So on the left side, the contour shows the expected host location after a separation of nearly a decade, and no host star is detected. So the team concluded that the host star is a white dwarf. And on the right hand side, one of my own publications last year, where we did not detect the host star flux after the event, and which allowed us to infer the planet host to be a white dwarf. And what's really interesting about this event is that the planet is around 2 Earth masses with an orbit of around 2 AU. So if you accounting for the mass laws, we would expect the planet to be more or less around 1 AU when the host star was still a main sequence star. So, which would have been analogous to the Earth's final fate. But I guess if there were any life on that planet, then it would have been destroyed. So I would not expect to find any life on that planet. Anyways, so that brings me to the project that I've been leading since my first postdoc at UC San Diego. Tentatively we call this project Rogue Planet Host Search. The goal is to detect or rule out host stars for most microlensing free-floating planet candidate detected to date using calculated star adaptive optics. And there's around 20 to 30 of these candidates detected to date. And for the last 2 semesters, we basically observed most of them already. And surprisingly, we detected host candidates for approximately half of them. And we propose for 1 more semester next year in order to characterize these host candidates. And here I just show a preliminary result for one of the really interesting cases. So in the center is the microlensing source star. And you can see a tiny little blip to the lower left corner, which is the host candidate we detect. So we utilize some of the post-processing algorithms from high contrast imaging for optimal PSF subtraction. So the center panel shows gas-up model built from other stars in the image. The rightmost panel shows the microlens source star subtracted, revealing the host candidate, which is separated at approximately 100 milliardsecond away from the source star. And one point to emphasize here is that unlike bound planets, at the time of the event, the host star, if there were a host star, then it's not expected to align perfectly with the source star. On the other hand, the planet was the mass that magnified the source star. So the planet is supposed to align perfectly with the host star. So that provides an opportunity to determine the planet projected separation, basically using multi-epoch imaging to measure proper motion. So next year, we're going to observe this event again, and then the proper motion will allow us to predict the host candidate separation between a host candidate and the source star at the time of the event nearly 2 decades ago, which will allow us to constrain the planet's orbit. So hopefully I will have a more detailed report at next year's symposium. Thank you.
Thank you so much. Any questions for coming? Yes?
So thank you for a very interesting talk. Can you comment on the metallicity, age, and other properties of these free-floating planets?
So for the free-floating planet detected by microlensing, there is very little information we know. We don't even know for most planets, we don't even know the mass and the distance. So all we know that, so typically the source star that got magnified is in the galactic bulge, this is around 8 kiloparsec, and the free-floating planet candidate is anywhere between 1 or less than 1 kiloparsec and 8 kiloparsec. So even the planet mass is only inferred to an order of magnitude. So that's I guess that's one of the limitations. But then I just want to mention that there's an opportunity to measure the mass for these objects in the era of Roman. Basically, if you observe the same event from Earth, the peak will occur at the event will occur slightly differently due to parallax events, and that provides a different another mass distance relationship. So we would have some of these candidates, at least with the mass measurement, but for more detailed characterization, it'll be more difficult compared to the other techniques.
Thank you. Any other questions? I would like to ask one. I've heard some estimates that from Roman, in principle, we could get very, very high yields on the number of free-floating planets that we could detect. Do you agree with this? Like, I'm just curious what your thoughts are on what Roman will tell us.
So yes, so some simulations have predicted more than 1,000 free-floating planet detections with Roman, with the caveat that we really know little about the free-floating planet mass distribution. We expect, so as far as free-floating planets around Neptune mass, so ice giant free-floating planets, that's relatively precisely constrained to around two planet candidates, I should emphasize, per star. But what's really uncertain is the sub-Earth regime. They're really difficult to detect, and we've detected 2 already with current generation ground-based surveys. And the inferred frequency for these sub-Earth free-floating planets varies by an order of magnitude. So basically, that's why current predictions for the Roman yield differs by so much. But I guess we'll soon have an answer. Maybe I think within the first season of Roman's observation, I think we'll have much refined and estimate of that number.
That's great. Oh, we have one more follow-up.
Thank you for the interesting talk. I'm curious about recently there are some discovery of free-floating planets in molecular clouds. How does those free-floating planets differ from the microlensing ones?
So thanks for the question. So both statistics from microlensing surveys and some of the planet synthesis papers I've seen, they predict that most free-floating planets should be of Neptune mass or maybe sub-Mars mass. I think most directly imaged free-floating planets are gas giant planets. So these are actually the rarest object we expect, and it's actually confirmed by microlensing. The mass distribution constraint from microlensing surveys is also consistent with very little gas giant free-floating planets and a whole bunch of ice giant planets. So I guess if directly imaging sensitivity directly to continue to improve, then that will suggest, I think, that the directly imaged FFPs would increase by a huge amount.
Okay, great. Let's thank Hemming again. And now is going to be our schedule change. So now we're going to hear from Jaren, who's going to tell us about exoplanet yields with the Habitable Worlds Observatory. So Jaren, when you're ready, you can share your screen.
Awesome. Thank you very much. Let's see. All right, third time's a charm. I'm seeing presenter view. Let's go. All right.
Yeah. Woo, looks good.
Let's see. 1 sec. Just going to set up a timer for myself because I don't know if anyone else finds this relatable, but ranting about things that you like is pretty easy trap to fall into. I also, before I get started, I wanted to extend a huge thank you to the program leads, the people organizing this awesome symposium. I really wanted to be there with you all in Baltimore, listening to all these great talks, but had a bit of a family emergency on Friday, and so I couldn't quite come make it. But thank you very much for accommodating the change, and happy to talk about the research I've been doing over the past year. So I'll get started. Today, we're going to be talking about some integrated science and engineering analysis. Over the past year, I've been working with a team to connect nuanced polarization effects in astronomical telescopes directly to some kind of science metric, which in this case was exoplanet yield, so that we can help to refine the design of NASA's Habitable Worlds Observatory. So for those of you who don't spend your times thinking about space telescopes 30 years in the future, NASA's Habitable Worlds Observatory was a recommendation by the decadal to, in part, detect and characterize 25 potentially late habitable worlds around other stars. Now, this requires an insane instrument sensitivity, and so at these sensitivity levels to detect these planets, we will observe this effect where the telescope itself will slightly polarize the incoming light, resulting in this effect called polarization aberrations. How this limits direct imaging, or coronography, is that polarization aberrations tend to be of low spatial order, and they tend to be really, really faint, kind of like the exoplanets we're trying to detect. And so what we see is that in the invisible light, polarization aberrations will manifest as this uncorrected halo around the inner working angle that is right around where your exoplanets would be and about as bright as your exoplanets would be, making them a little deleterious potentially to the future of Habitable Worlds Observatory. So we really wanted to try and constrain this effect. This effect arises because, telescopes are these geometric structures. And whenever polarization occurs at every light-matter interaction that occurs with some material at a non-zero angle of incidence. So the diagram on the right just sort of shows light coming into some like air dielectric interface. This can be dust, this can be a telescope mirror, whatever, right? And because on telescope mirrors like the ELT, you can see on the bottom left here, have varying angle of incidence, we get varying polarization across the beam. Now, in graduate school, I wrote this food-based Python package inspired by the Suisan fish market in Hilo, Hawaii. It's called Poke. And last symposium, y'all gave me some really good recommendations for other food-based packages that I reserved on my GitHub, so thank you for that. But the goal is to be able to open source this polarization ray tracing algorithm so that you can actually simulate these effects in astronomical telescopes and integrate them into other analyses. This led to the project that started roughly a year ago, actually, where we tried to model high-order wavefront sensing and control in a realistic model of a coronagraph behind a kind of early Hab-Worlds point design subject to these polarization effects to see how sensitive the coronagraphs are to this. The team that conducted this is pretty large in terms of the number of collaborators, but the people that met weekly to debug our code and make sure that we were doing everything correctly are shown portraits here. There's myself, Brianne Satarski, the deputy principal architect of Hab-Worlds, Chris Stark and Scott Will at NASA, and Max Miller-Blancher, my advisor at UCSB. And our goal for this year-long study was to construct an integrated modeling pipeline to trace these tiny polarization effects all the way into likelihood of detecting Earth-like exoplanets using exoplanet yield calculators. And so the simulation pipeline we came up with is this. I just put this up here for the people that care about kind of the optical modeling nuances like myself, but won't go into too much detail. Essentially, I created a Hab-World tailored front end for Poke that rapidly generates the polarization aberrations, sends them to a diffraction simulator that was built for NASA's Habitable Worlds Observatory, and we added effects like polarization aberrations, imperfect surfaces on all of the optics, some static segment misalignment in the primary mirror, and then conducted high-order wavefront sensing and control simulations. So we wanted to do this as high fidelity as possible. The coronagraph that was baselined for EAC1, or the first of these kind of early point designs to do some pipe cleaning for the Habitable Worlds Observatory design is an amplitude apodized vortex coronagraph. So it takes this segmented aperture, applies a really funky grayscale apodizer that you can see in the center of this slide to kind of desegment the aperture, and then propagates that through this vortex coronagraph, which are known to have pretty high yield. One huge assumption that this study makes, because it was the assumption made for EAC1, is that it assumes an ideal achromatic and scalar vortex masks. Now, vortex masks are notoriously not necessarily achromatic and not necessarily scalar. There's really excellent work being done by Dr. Niyati Desai and the soon-to-be Dr. Skylar Palatnik trying to realize masks like these using various technologies. But this was the assumption we made for this run of analysis. And this coronagraph was cooked up by Susan Redmond and Dimitri Mawe at JPL. And so, armed with this modeling pipeline, we sought to answer the question: how does the distance between the primary mirror and secondary mirror of a HabWorlds-like point design trace to polarization aberrated contrast, or the light field that you end up getting that you can't correct? And so I put my undergraduate lens design hat on, and I cooked up a bunch of different optical designs for this Habitable Worlds Observatory architecture, where literally we just shrink the barrel a little bit. We tried to explore a pretty massive trade space. I won't be showing it all here, just because a lot of them tell the same story. We looked at 2 different coding recipes for the primary and secondary mirror, 5 different bandwidths shown in various colors there. We traced 5 wavelengths per band and 10 total different optical designs, going from the nominal kind of 16-meter separation all the way to a much shorter separation, about 7 meters, which is pretty unrealistic. But we wanted to see how far it could go. This results in roughly 500 high-order wavefront sensing and control simulations, which would melt my computer and be a space heater in my house that my poor wife and dog would be subject to. And so we wanted to try and figure out a way to do this more efficiently. And so largely Scott will, but the rest of the polarization PSDD actually analytically derived what a focal plane wavefront sensing algorithm that a coronagraph would use to, stay dark would sense under polarization aberrations. This is specifically for pairwise probing type estimators. And so what we can do is apply high order wavefront sensing and control, do the full simulation for a case without polarization aberration, apply the small amount of polarization aberration that we expect calculated by Poke, and then apply this correction, which is really, really accelerated our ability to explore the solution space. And so that paper is sort of forthcoming in Optics Express that shows this result. The resulting focal plane, because this control is ideal, we say sets the lower bound. Like, no matter what you do, you cannot do better than this. And so this allowed us to do that rapid solution space exploration. And so we come to the first suite of results. This is just kind of a azimuthally averaged radial profile of what one might see if looking at an unpolarized star with this EAC1 design. Each of the curves represent a slightly shorter barrel as you go to a lighter color. And I've put 2 exo-Earths at 10 to the minus 10 normalized intensity to show sort of where you cross the threshold of the polarization aberrations being greater than the exoplanet. And what we can see is that the bottommost colored curve in dark blue, which is the nominal EAC1 design, was pretty conservative. Granted, there's a lot of things about this analysis that are ideal, but we don't necessarily think that visible will be the polarization aberrations will be super limiting in the visible here, subject to the assumptions in this analysis. In fact, if we were in an ideal world, we could go to 12 meters. But this really is just trying to illustrate that we have this analysis suite that can be used and is being used to further refine designs in advance of Habitable Worlds Observatory. The next sort of feature of interest that I wanted to highlight is the ultraviolet. So this is the same plot, just we basically have the wavelength going from 550 to 250 nanometers to see, you're approaching the ultraviolet, you want to characterize that ozone feature. How bad are the polarization aberrations there? We generally know that they get worse as a function of a shorter wavelength, but how bad is that? And what we see on this figure is that the chromatic scaling of the point spread function actually really works out for us. If you have your wavelength, your diffraction limited point spread function is half the size. And we know that polarization aberrations mostly arise near the inner working angle of your coronagraph. And so it's really important to consider both the diffraction scaling in lambda over d, of the coronagraphs, but also the on-sky scaling to actually trace these effects. Because what we find is that we really don't expect polarization aberrations to be that limiting in the visible. There may be other effects that limit contrast in the ultraviolet, but it's seeming like the UV may actually have an easier time than the visible because the diffraction limited point spread function is smaller. And so these are just kind of the takeaways. We expect the most sensitivity in the visible. We maintain 10 to the minus 10 normalized intensity in this analysis for a 12 meter barrel. And we really have to be aware of cases where planets are really close to your inner working angle, because that's where polarization arises. This analysis was repeated in the infrared, but more or less told the same story. It's just the effect is lesser, and so you can tolerate more. And so visible tends to be the most sensitive. Now, given that we can generate all of these point spread function profiles with this highly integrated analysis, we wanted to take it one step farther and ask the question, is exoplanet yield insensitive to polarization aberrations? And so we conducted some exploratory yield simulations with Chris Stark's Friday, which is a remote deployment of his altruistic yield optimizer, which is a tool that optimizes the design reference mission of Habitable Worlds Observatory, or of any telescope, but in this case, HabWorlds, in order to use things like exposure time, number of revisits, that kind of thing, to maximize the likelihood of detecting a planet, given that a planet is around a system. And so we added this to our pipeline to close the loop to exo-Earth yields. And just as a quick introduction to the kind of outputs, just in case people don't live in exoplanet yield space, each of these points on a yield plot represent an extrasolar system. The x-axis is the distance to the system. The y-axis is the star's luminosity. And what we're going to be looking at is habitable zone completeness, or the probability of detecting an exoplanet given that it's there, because it drops a planet there to see if you can detect it. And so we can look and generate multiple yield plots and try to compare them by eye. I prefer them by looking at the element-wise difference of the unpolarized and polarized case in order to see what contribution polarization aberration is making to this. And so for the nominal EAC1 configuration, we only see a 5% degradation in yield. It's pretty modest. And we see that the cases near the inner working angle have a lower completeness, less likelihood of detection, and it spends more time. Sorry?
Go ahead, you're good. Maybe
Sorry.
2 more minutes.
Thought I heard something. Yeah. Much appreciated. Smaller angular separations and brighter stars, it spends more time trying to characterize those to maximize completeness. And then as we go to shorter cases, here's the 12 meter barrel, we see a slightly greater yield degradation, but still pretty modest relative to the previous, where actually the exoplanet yield optimizer is trying to spend more time at targets near the inner working angle to maximize yield. Now, if we do a bunch of these analyses, where each of the red stars corresponds to a yield simulation, and each of the blue dots corresponds to contrast at a given annulus in lambda over d, what we see is this linear trend in contrast as a function of the kind of barrel length, but change in angle of incidence, and also more or less linear yield plot, except for in the small barrel length change case. And so this region on the left, where you're not departing too much from the nominal design of EAC1, is where we see the yield calculator actually actively compensating for polarization aberrations, meaning that there is a regime where yield can compensate for this effect that we can't correct with AO systems. And so I'll skip through the future work just because it's been 13 minutes. Basically, we might be extending this to work on a spectral polarimeter that is proposed for HabWorlds. We're running a coronagraph design study to further see where we can maximize throughput in the ultraviolet, given that you have a smaller point spread function. And I'm working with Dr. Dan Shanks at JPL to design polarization aberration compensators, should they be necessary. Mahalo very much. I hope you all have a wonderful symposium.
Thank you so much, Jaron. Any quick questions? Yes.
Hello. This is Janice Lee. I have a question about the assumed point spread function in the UV. The diffraction limit is assumed, it's the requirements at 5,500 angstroms, right? And there's going to be some degradation. You're not going to be diffraction limited in the UV. So what point spread function are you assuming?
You're absolutely right. Yeah, so we are assuming that the adaptive optics system is capable of correcting the scalar wavefront error down over the control region that it's capable of controlling. So like half the actuator spacing in lambda over d. So even if you're not diffraction limited in the ultraviolet, because the requirement, like you said, is diffraction limited in the visible, you can still clean it up with stroke on your deformable mirror. And so that's why we ran the high order wavefront sensing and control simulation.
Okay, thank you.
Okay, great. Let's thank Jaren one more time.
Thank you very much.
And now we have our final presentation for this first day of our symposium. Lily Zhao. Let's see, you're right here.
It'd be really great if you could advance my slides too. Super appreciate it.
Oh, you're too kind. Perfect.
Bigger.
Yes. Perfect. Amazing. So Lily's going to tell us about stellar signals in spectra.
Thank you. Yeah, I know. I was like reading the program and I saw my title and I was like, what does that even mean? Like, did I submit this? And so I think what happened is I was like trying to be funny and I like made all the words start with S. It was going to be like a joke, but then I like lost steam, I guess. Anyway, so I'm so sorry for the really bad title. I'm sorry for starting after 5, but hopefully I can convince you that this is like a really cool idea and make up for the bad title in the subsequent slides. Some more S humor for you. Okay, so we've had all these great talks about our exoplanet detection. My chosen poison is the RV method, right? We measure a star moving around its common center of mass with the planet by measuring the Doppler shifts in its spectra as it changes with respect to time, and it looks like that. And so something that we use a lot in the RV world is this idea of semi-amplitude, or K, which is kind of like a measure of the amplitude of the signal that we're looking at. So for example, if we want to find Earth mass planets, that corresponds to a K of 10 to 30 centimeters per second. And so if you have the ability to measure something at this level, 10 centimeters per second, we call that extreme precision radial velocity, or EPRV. And so this is, like the field that I work in specifically is trying to aim at getting 10 to 30 centimeter per second RV capability. And this is something that I think is really important to do within the next, I'll say, 3 to 5 years, because EPRV is really what we're going to need if we want to detect a plethora of Earth mass planets. And so we've heard a lot about great detection methods. Here I'm showing planet mass as and separation on the x-axis, the detected planets as dots with some solar system planets for reference in green, and a few different detection limits. So for example, Gaia is going to do great work and explore a range of parameter space we haven't seen before, but it's simply just not going to have the sensitivity to find Earth mass planets. We're not going to get there with ground-based direct imaging. I love that Jaren is perfectly, personally making sure that we'll get there with Habitable Worlds Observatory, but to use a space-based mission of that grandeur to do a blind search for planets would be just so heinous, in my opinion, that I really think the better plan is to find some Earth mass planets so they can focus on deciding the habitable part rather than the world's part of that mission, right? Okay, so you're like, wait, Lily, wait, look at this transit curve. Look at how close it is to the Earth's, right? And so it's true, space-based missions like Kepler and upcoming missions will be sensitive to Earth mass planets. But what this plot isn't reflecting is transit probability, which drops precipitously with separation. And this is a non-negotiable geometric constraint, right? There's nothing we can build, there's no machine learning we can use that will make these planets transit their stars. And so if we want to find a statistically significant amount of Earths, if we want to put our Earth in context, if we want to have them around bright stars that we can follow up with HWO, EPRVs is the way that we're going to do it. But we'll get more than just finding these lower mass and longer period planets and high priority targets for the future. We'll also learn more about these planets by getting RV measurements of them. We've already found that with greater RV precision, we're finding planets that we've previously missed in multi-planet systems, and so we get a better dynamical picture and constraint on how these systems look. If the planet also happens to transit, we can also figure out their orbital alignment, which gives clues to how planets migrate and change as they form. If we also know their size, we can figure out their interiors because we can calculate the density of the planet. And of course, for any atmospheric work, you have to know the mass of the planet, so then you know what portion of what you're looking at is made out of planet versus atmosphere. And more recently, people have been using the kind of high resolution spectra we get with RV instruments to characterize the atmospheres themselves. Okay, so great. RVs are great. I think we can all agree. And it's great because Doppler shifts is something you learned in high school physics, right? We just measure it going back and forth, and maybe this is a little bit smaller for Earths, but it's like fundamentally the same, right? No, because of course, stars do not look like this friendly yellow spot that we have on the screen. Stars look like this. And so stellar variation from all of this nonsense is now the largest source of RV error. And it's complicated because it comes in a lot of different flavors and a lot of different forms. Stars themselves oscillate on the time scale of minutes. We're kind of the main sequence stars that we're interested in serving as planet hosts, and that'll introduce an RV error of about 0.1 to 1 meter per second. There's also this granulation feature that can change the shape of spectral lines. And as that changes on the time scale of minutes to hours, or in the case of supergranulation, even days, that also introduces some RV scatter around 1 meter per second. And lastly, we have these activity features, so these like darker sunspots or brighter plages and faculae, and those can persist for up to even years. And depending on how fast your star is rotating, those can introduce RV shifts of up to 10 meters per second, which is quite a lot bigger than 10 centimeters per second. And so this is a difficult thing to get a grasp on. Lots of things seem to be changing. Lots of things it's really difficult to, for example, simulate this completely. But something that I've been working on recently is this idea that even though it's very complicated, the idea is that all of the changes that you get from all of these different contributions is still compact. And so what that means is that you can use a small number of basis vectors to represent all of the changes of interest. And though this might sound crazy, I think I can convince you. Because if you think about it, let's go through this thought exercise where instead of considering the star as a whole, we consider these little patches across the stellar surface. And so each patch will give rise to its own special spectra. And if you add up all of the patches, you get the spectra you'd get from the integrated star. And each patch will have certain relevant parameters that decide what spectra it's giving rise to. It's going to have a given RV shift, because maybe the ones in the middle are oscillating towards and away from you, while the ones on the side are doing less so because of the bicosine theta. And of course, the star is rotating. So these will be blue shifted as they rotate towards you and away, right? One dimension, RV shift, blue shift or red shift. They'll also have different spectral components. So maybe different realizations of granulation will have slightly different line shapes. Spots might have the spectral component of like a much cooler star versus brighter plages. In fact, they might have a brighter one. And those changes might seem very complex, but there's been work in the field, for example, Melissa Ness's canon, that suggests that even those spectral changes can be represented by a low-dimensional representation. So not one-dimensional, but low-dimensional still. And then lastly, we have intensity. And so spots will be darker. The ones on the edge that are limb darkened will also be slightly lower intensity than other parts, but again, a one-dimensional metric. And so really, if we count these up, we don't get that many dimensions. And so I think compact is still worth it. But we can talk and we can think about it all you want. So we decided to instead run like a sort of like little sandbox toy model to see if our approximation even holds. And so here for our star, we're using just one quiet spectrum to be most of the star. And then we're assigning a spot spectrum to parts that are shown as activity features. And we're also considering the effect of these activity features rotating in and out of view. And so we're using this very simple two-component model. But you can see how the other types of stellar signals can fall into these categories. Different realizations of granulation might just be a different type of different spectrum. Oscillations would just be a different type of rotation, and so forth. And so we can take our spot map, assign the different spectral components to the different spots, and mock what the resulting observations would look like, which will denote x sub n. And so if we look at our two-component model, we can construct a basis vectors that we think will be sensitive to the stellar changes that we care about. So first, we can simply take the quiet spectrum and subtract it from the spot spectrum, and that'll give us a basis that's sensitive to the amount that this observation is different because both of these components are present. And for the second basis vector, we'll take the quiet spectrum and we'll subtract the shifted spot spectrum, which will give us a measure of how this observation is different because there's a spot rotating in and out of view. So if we take our observations, our x sub n, and project them onto these basis vectors that we've constructed, they should tell us something about the visible spot fraction, how much of that second spectrum we're seeing, and the Doppler distortion, how much the spectrum is changing because the spot is rotating in and out of view. And so if we look at this example here, I'm showing for one star, which has a spot rotating in and out of view, and the consequent RVs that result. If you project it into this basis space that we've constructed, you see this really coherent, like heart-shaped loop, right? And in fact, if you repeat this with spots of different sizes, so increasing radius on the x-axis, and different position, increasing latitude on the y-axis, you see that they produce these coherent loops that change as a function of what the spot looks like and where it is. And so this suggests that if we're smart about the parameter space that we're working in, we can use the spectra that we're observing to hunt for planets and actually learn something about what the surfaces of the stars look like. And we can stop making star people angry by calling their field noise, right? We can use the data that we're already collecting to learn things about main sequence stars that would be hard to image otherwise. But okay, I'm still a planet scientist for now. And so how can we use this to correct for the RV signals that we're seeing because of the stellar activity? So same grid of stellar spot properties. Here I'm showing in black the RVs that result because we have this variation on the stellar surface. And if we use these projections as labels to regress their RVs against, we can correct out the stellar signals, and we get these yellow curves instead. And so if we zoom in, here I've shaded in green the 10 centimeters per second, just kind of give a relative scale. And you can see that the residuals are on the order of 20 centimeters per second. But this is the case of just the star, no planet. If we repeat this exercise where we've injected a planet signal, you can see that we get completely comparable results. Because we have constructed a basis space that is intentionally sensitive only to the spectral changes due to these stellar variations, the stellar variations get removed and the planet signals remain. And so I'll just summarize with this last slide. We really need to develop precision RVs because that's the way that we're going to detect and characterize Earth twins to understand our planet and get to like the biosignatures that we don't feel the need to apologize for, maybe. Stellar signals are now one of the biggest things that we have to be concerned about in the quest for 10 to 30 centimeters per second RV precision. And if we use all of the data that we have from spectra, every single pixel that we're collecting, and we construct a smart enough basis vector space to capture all the changes of interest, we've shown that we can use just a low-dimensional representation to get the scatter down already to 20 centimeters per second. And so moving forward, this was just a simulation to prove that the assumptions that we were making proved true and would be useful. We'll be moving to real data next, and we'll be trying both like physics-based basis vector construction, which is kind of like what I talked about before, knowing what the spot or what the different components should look like. But there's also a lot of data-driven things that we can consider as we I don't know, use principal component analysis. We can maybe get tricky with some machine learning, things like that. But I think the next step will be moving to real observations and exploring different ways of constructing this parameter space. And so I'll end there, and I'd be happy to take any questions. Thank you for your attention.
Thank you so much, Lily. Yeah.
So this is a really, really great talk. And my question is about this last section of future steps, right? So for M dwarfs that are super, super variable, right? This technique is still going to be viable for being able to capture some of the activity.
Yeah, so that's a good question. I like answering questions about future work because I can say whatever I want, right? But I think there is hope with M dwarfs. Like you were saying, they're so variable. And so if you use something like PCA, where the variation is dominated by these activity signals, the PCA will be more sensitive to those stellar changes. And so it could possibly be like, I think ultimately the correct method will depend on what star you're using and the relative amplitude of the stellar activity and the planet activity. And so when I'm constructing target lists, I think it's a mistake just to get stars with like that are quiet or things like that. I think we also need things like M dwarfs that are very active, that are showing these large things to kind of understand what the basis space should look like, if that makes sense.
Yeah.
What about uncertainty quantification? You're doing a projective measurement by doing this PCA projection, but your much larger uncertainties get the fact that the star is doing all this nonsense with the spots. Does that come through in your analysis method?
That's a good question. We do consider data uncertainties in the simulations that we've run, but we haven't characterized the uncertainties of the corrections. There are some ways that we could do that. For example, we could like bootstrap, right? We could do like MCMC and things like that. But I think the answer to your question would be to repeat this with solar data, which would be the next step, because it's something that that has real data properties and has all this nonsense that maybe we're not considering, but also has NSO data that tells us what the star looks like and gives us kind of this image over here. And so if we start there, use that to kind of constrain how well our method is performing and get metrics of performance that way, we can possibly port that to other stars and also see how applicable they are to like M dwarfs and stars of other spectral types.
Awesome. Thank you so much, Lily. And let's thank all of the speakers and our Are there any announcements for tomorrow, or are we good to go? Oh,
Yes.
Okay, we have one announcement. We're going to be posting a spreadsheet to sign up for activities for the free afternoon evening on Wednesday. And we kind of need to know who is going to be interested in doing what so that we can figure out, how to get where we're going and make reservations for places and things. So we'll post that tonight on the probably the Fellows Slack channel. And yeah, just put your name next to one of the 3 options that we're going to list.
awesome. Okay, great. See you all tomorrow morning.